In this video, I'm going to show you how to solve the trigonometric equation sine of x equals constant in the domain 0 to 2 pi. So here we've got a problem. We want to solve sine of x equals root 2 over 2. And in this problem, we're going to be working in degrees. X is between 0 degrees and 360 degrees. So here's a graph of sine of x. The graph y equals sine of x. And we are looking for where this graph intersects the line y equals root 2 over 2. So that's what we want sine of x equals to. And root 2 over 2 is a little over 1/2, so we'll write it over here. This is root 2 over 2, and we'll draw the line here. So this is the line y equals root 2 over 2. Okay. So now we want to see where this intersects. Well, we've got quite a few points of intersection. We've got 2 here, 2 here. If we extend the graph of sine on and on, we'll keep getting 2 points of intersection on every hump above the x-axis. So there's infinitely many solutions, but in particular, we're interested in solutions where x is between 0 and 360 degrees. So here's 0 here, and here's 360 degrees here. So we're looking at solutions in this box right here. So we've really just got 2 solutions that we're interested in. We're interested in this solution here and this solution here. So how do we find these solutions? Well, remember that if you have sine of an angle equal to something and you want to figure out what that angle is, then you can just use arcsine. So that's going to give us one of these solutions here. And then we can use that solution to find the second solution. So let's go ahead and do this. So using arcsine, this gives us what's called our principal value. Principal value. And that tells us the first solution, we'll call that x1, equals arcsine of root 2 over 2. Just applying arcsine to both sides here, that cancels out the sine. And we just get x1 equals arcsine root 2 over 2, and that's just equal to 45 degrees. If you punch that in on your calculator, that's what you'll get. And so 45 degrees, we can tell that corresponds to this solution up here. Great, so we've got one of these solutions, but how about the other solution over there? So the question that we need to ask ourselves for this other solution is, what other angle between 0 degrees and 360 degrees has the same value of sine? And to answer this question, we can turn to the unit circle. So let's draw a little sketch of the unit circle down here. So put some axes, put a circle on those axes, and okay. So we know that our starting angle is 45 degrees. Let's draw that. So 45 degrees right here. That's x1. So let's put x1 equals 45 degrees. And now we want to figure out what other angle has the same value of sine. So let's think about our cast diagram here, CAST, which tells us where various trig functions are positive. So we want to find where else sine is positive. Sine is positive here because all are positive, and we want to see where else is sine positive. Well, S, that stands for sine, so it's also positive in this quadrant. So we also want the angle that is right here with still a reference angle of 45 degrees here. You can also think of it that these two angles have the same y coordinate. If we draw a little dotted line across, they reach the same height, and sine is just y. Either way, you'll come to the conclusion that this is the other angle that we want to find. This is our x2 angle. So how do we find our x2 angle? How do we find that angle? Let's write it out over here. So this will be our second solution. Second solution. And that second solution is that x2 equals what? Well, we know that all the way around to the x-axis again, all the way around from here to here, that's just 180 degrees. So we can use our reference angle of 45 degrees and go backwards 45 degrees, and that'll get us just part of the way around. So x2 is just 180 degrees minus 45 degrees, which is just 135 degrees. So 135 degrees is that point right there. Okay, cool. So now we've got our overall solution. Our overall solution is just 45 degrees and 135 degrees. So x equals 45 degrees, 135 degrees. And remember, that's just for x between 0 degrees and 360 degrees. If we didn't have this limit here, if we didn't have this particular domain that we're talking about, then we'd have infinitely many solutions. But we're only interested in x between 0 and 360, so that's why we only have these two solutions right here. Alright, so here's another example, and this example is going to be pretty similar, except now we're working in radians, 0 to 2 pi, and also we have an equation that's not yet in the form sine of x equals constant. But that's okay, because we can convert this equation into a form sine of x equals constant, and then proceed like we did before. So let's first manipulate this equation to get it to the form sine of x equals constant. So let's get the sine of x alone on one side, subtract 1, we get negative 2 sine of x equals negative 1, and then let's divide by negative 2, and we'll just get sine of x equals 1/2. Great, so now we've got our equation, sine of x equals a constant. In this case, the constant is 1/2, and we have to go ahead and solve this using the same method as before. So we've got our graph y equals sine of x, and let's see where it intersects. Y equals 1/2, so 1/2 is right about here. Sine of x ranges between 1 and negative 1, so 1/2 is about halfway up there, 1/2. So this will be our line, y equals 1/2. And it intersects in a couple different places like before, infinitely many actually if we extend sine as long as it can go. But here we're just interested in x between 0 and 2 pi. X is 0 is right here, and x is 2 pi is right here. That's just a single period of sine. So we're interested in the solutions within that box there. And so again, we've just got two solutions here. This one and this one, 2 points of intersection. So let's go ahead and find the first point of intersection. And we'll do that just like before. We'll just take the principal value. So the principal value, remember that's just what we get when we use arcsine here. So x1, our first solution here, is arcsine of 1/2, which is just pi over 6. So pi over 6 is that solution up there. And then for our second solution here, we need to ask what other angle between 0 and 2 pi has the same value of sine. So let's write that down. What other angle between 0 and 2 pi has the same value of sine? Well, we can answer that question again using a unit circle. So let's draw our unit circle. And okay, let's plot this angle here. That's pi over 6. So that's about right over here. Pi over 6, that's our solution, x1, our first solution. And let's draw our cast diagram, because we need to figure out what other angle between 0 and 2 pi has the same value of sine. Well, here sine is positive because all trig functions are positive. And so where else is sine positive? Well, it's just in this same quadrant again. So we're going to be looking for a solution. We're looking for an angle which mirrors this angle, but in this quadrant. So our second solution is all the way over here. And our reference angle here is still pi over 6 because it's nice and symmetric. You can also think that these two angles, they have the same value of sine because they have the same y-coordinate, and sine is just the y-coordinate in the unit circle. Okay, so bottom line is we just need to figure out what is this angle x2, and that's going to be our second solution. So let's write down second solution. Our second solution is x2, and that's equal to, well, again, if we just want to go part of the way around, we can think about going all the way around half circle. Half circle is just pi, so pi, and then take away that pi over 6. Take away the pi over 6, and that gives us the almost all the way around, but leaving pi over 6. That's the angle that we want. Okay, so that's just, pi is just 6 pi over 6, so minus pi over 6 is just 5 pi over 6. There we go. And that is our second solution up there. Okay, great, so we've got them both. Our overall solution is x equals pi over 6 and 5 pi over 6. And that's it, we're done. Remember though, that's just for x between 0 and 2 pi radians. If we didn't have this constraint, we'd have infinitely many solutions because there'd be 2 solutions every time sine has a hump above the x-axis. But we're just looking at the domain 0 to 2 pi, so just looking at these 2 solutions right here. Here's our final example, and we want to solve root 3 plus 2 sine x equals 0 on the domain where x is between 0 and 2 pi. So this is kind of like the previous problem. We'll just go ahead and rearrange this into an equation, sine of x equals constant. That'll be our first step, so subtract root 3, and we get 2 sine x equals negative root 3, and then divide by 2, and we'll get sine of x alone. We get sine of x equals negative root 3 over 2. Okay, so now we just need to put this on our graph of sine of x. This is our graph y equals sine of x, and negative root 3 over 2 is pretty close to negative 1. It's a little bit above, a little bit closer to 0. Put it right here, negative root 3 over 2, and let's draw that line just to get an idea of what this looks like graphically. So that's the line y equals negative root 3 over 2, and we want to find where this line intersects with sine of x, but we're just looking at the domain as x goes from 0 to 2 pi. So x is 0 is just the y-axis here, and x is 2 pi is right over here. So we're just looking for intersections within this box here. And here we see that there are 2 points of intersection. There's a point right here and a point right here. So like before, when we wanted to find one of the points of intersection, we just used the principal value. So we'll do that again. The principal value, that's just the solution that we get when we apply arcsine to this equation. So our first solution will be arcsine of negative root 3 over 2. So everything seems pretty normal, pretty similar to how we've done the previous examples. But hold on, we take arcsine of negative root 3 over 2 and we get negative pi over 3. Now this looks a little different. Usually the arcsine would just come out to an answer that is between 0 and 2 pi. But now this answer isn't even in the domain that we wanted. So what do we do here? This answer is actually this point right here, but we just want these 2 points. Well, what we can do is we can get an equivalent angle. We can get an equivalent angle to negative pi over 3 by just adding a full revolution around the unit circle, which is 2 pi. So let's just add 2 pi, and then the result will be in our domain. So 2 pi minus pi over 3, 2 pi is just 6 pi over 3, so minus pi over 3 is just 5 pi over 3, and that's a little bit less than 2 pi. Great, so that's all is better now. So that's this point over here. And now to get the other point, we just ask the same question that we've been asking in the previous two examples. What other angle between 0 and 2 pi has the same value of sine? So let's set up a unit circle to help us answer this question. We'll draw the unit circle, and we'll draw our angle here, 5 pi over 3. That's about here. We go around this way. That is x1 equals 5 pi over 3. Okay, now we want to find what other angle has an equivalent value of sine. So let's put our cast diagram, C-A-S-T. That tells us, yeah, sine is negative here because cosine is the only one that's positive in this quadrant. And where else is sine negative? Well, all are positive here. Sine is positive here. Tangent is the only one that's positive here, so sine has to be negative here. You can also think that we want something with the same y value, because y represents sine in the unit circle. So let's go ahead and draw that angle. We're looking for this angle here. So we want the angle that goes around to here. That'll be our x2. And in order to find that out, we can make use of reference angles here. The reference angle, well, the area between, the angle between here is just pi over 3. You can also think we had negative pi over 3 initially, so this is like going backwards pi over 3. And so the angle between here and here will also be pi over 3. So now we can say that our second solution is just obtained by going halfway around the circle. That's pi. x2 equals pi plus a bit more, plus pi over 3. And that'll get us all the way to our solution over here. So pi plus pi over 3 is just, well, pi is just 3 pi over 3, so this comes out to 4 pi over 3. And there's our second solution. Okay, great. So now we're done. We've got our overall solution. Our overall solution is just our two solutions here. Let's put them in order. We've got x equals the smallest one first, 4 pi over 3, and also 5 pi over 3. And remember, that's just for x in the domain 0 to 2 pi. If we didn't have that restriction, we'd have infinitely many solutions, but because we have this restriction, we only have 2 points of intersection. In the future, we'll also learn how to solve similar problems, but where the domain is different and where we use cosine or tangent instead of sine.